Hello, everybody, and welcome to this Smartcrete webinar on improving the durability of precast concrete culverts in infrastructure. My name is Gavin Chadbourn of Optima Asset Advisory, a small boutique consultancy focused on asset management and materials technology. I'll just start with an acknowledgement of country. I acknowledge the traditional custodians of this country and their deep continuing relationship with the lands and waterways on which we meet. I pay my respects to the elders, past, present, and emerging, and recognise the strength and resilience of Aboriginal and Torres Strait Islander peoples. Okay, we have two presentations today from the project proponents, BG&E and Curtin University. The first presentation will set out the background and drivers for the projects and the issues that were intended to be addressed. And the second speaker will talk about the work undertaken to date and the progress and status of the project. The format of the webinar will be we will have both presentations back to back, and then a question and answer at the end. So all the questions will be saved to the end. If you have any questions that arise during the presentation, could I ask that you type them into the chat, just as a reminder. I will then collate all of those questions and read those out. When we do the question and answers, you can either put your hand up and I'll call you out and you can state your question. If you're a little bit shy but still have a question, put it in the chat and I'll do with that. Just for your information, this session will be recorded and made available after the session through the usual channels. I think it's through Smartcrete, and I think there's also a Smartcrete YouTube channel. Without more ado, our first speaker is Erica Smith. Erica Smith has worked in bridge engineering industry for over 30 years. She has experience in transport infrastructure management, inspection, maintenance, design, and assessment. Erica is currently an associate director with BG&E, but prior to this, she worked for Main Roads Western Australia for 24 years in a variety of bridge and major project roles. Her experience covers transport, resources, oil and gas sectors, and she has represented Australia and New Zealand on the World Road Congress. Over to you, Erica.
Hi all. Hopefully you can see my screen now, and I guess we're off. So my presentation today is more about setting the scene for the technical stuff to be covered over by Prabir with the three prongs of research that they're doing at Curtin University. So a few gory pictures and a little bit of background from me. So the problem, precast concrete culverts form part of essential transport infrastructure. They often deteriorate in service, however, before their expected design life. So older concrete culverts were generally cast in situ, and many suffered from cracking and spalling due to lack of concrete cover, ingress of moisture, and other sort of environmental aspects. Newer precast concrete culverts are generally more robust and they perform well, but there are still some reinforcement corrosion problems, particularly in the salt-affected areas of WA, which is where this project sort of concentrated its effort. In addition, once you then need to do some repairs, it's a little bit like putting a Band-Aid on it in some aspects. Concrete patching or crack repairs, they can be quite successful in the areas that you're looking at, but then other areas fail due to general dampness through porous concrete or lack of concrete cover. So the causes of deterioration can be many and varied, and I'll go through some of those in my slides. But as I say, Curtin University is looking at into some possible causes of that. BG&E's involvement, we value the opportunity to contribute to Smartcrete and the university research. We sort of commenced this project back in 2021, sort of forming the scope and the ideas behind what has emerged over the subsequent years. We're an industry partner on this collaboration, and basically what that means is we stump up some money for some testing, transport, materials, those sorts of things. We contribute hours for asset management specialists, so that could be structural engineers, material specialists, technical officers. So it's an in-kind sort of contribution. And we also provide those valuable connections to what I would term real life. And in this case, predominantly to Main Road's Wheatbelt region in particular, but also some of the concrete manufacturers as well. Before we get too far, I figured that we should make sure we're all on the same page regarding what is a reinforced concrete box culvert. Engineers aren't that don't have a great way with words. We talk about a box. Well, it looks like a box, right? This is taken from Main Roads inspection guidelines and shows the various components of a box culvert. The ones that we're talking about today and as part of the research are the precast reinforced box culverts. So there's barrels 1 and 3 here in this 3D visualization. What is a culvert? It's a buried structure that transfers something. That something can be things like water or stock or pedestrians or other things. And it carries something over the top. And again, that could be anything like vehicles or trains or pedestrians or whatever. And it's also designed to safely resist the earth pressure. So in WA's world, a box culvert is defined as a structure having only clear openings of less than or equal to 3 metres. If it gets bigger than that, they term it a bridge, and it's treated slightly differently in the vehicle permitting and asset management side of things for Main Roads WA. And obviously a box culvert is shaped into like a box. Not too hard to understand. Culverts are an important component of any road network. Compared to bridges, culverts are smaller and might be considered to be less critical. They're buried beneath the road embankment, often sight unseen. However, failure of culverts can be a hazard to traffic, and excessive settlement or collapse can result in closure of the network. So they still constitute an asset that is subject to deterioration, and they therefore must be managed appropriately. The size of the problem, the state of WA is pretty big and has nearly 186,000 kilometres of local and state roads. Main Roads WA looks after about 19,000 kilometres of those, which is just over 10%. There are nearly 28,000 culverts managed by Main Roads, so we have some decent records on that within the state. So that equates to about 1.5 kilometre culverts per kilometre on Main Roads network, or if you want to flip it the other way, about 1 culvert every 680 metres. And of those 28,000 odd culverts, 7,000 are what we're talking about today, which is precast boxes. So still a very large number. That is just on the Main Roads network. We don't really have a good indication of the total number of culverts in WA, but it's obviously far higher than that because you have culverts used for rail and roads managed by others, whether that's mining resource organisations, water corporation, local governments, and so on. So for Main Roads, again, because again, we've got a little bit more information about them, the total investment in their culvert structures is actually considerable, and it's comparable in value to that for bridges. So, and it's probably the proportion's likely to be higher for other asset owners because they generally have smaller structures in their bridge stock. Just having a look at some of those defects that I alluded to before. Defects in concrete are often related to lack of durability, resulting from composition of the concrete, poor placement practices, poor quality control, insufficient curing, or it could just be the environment, which is more aggressive in which it's placed. So cracking, everyone recognises that reinforced concrete cracks, and there will be some cracking, but it's those cracks that are bigger than hairline. So hairline is sort of considered less than or equal to 0.1 of a mil. They may be considered harmless structurally, But we still need to look at those because they may open up and progressively spread to longer and wider cracks and then become a durability issue. Corrosion of reinforcement is a big issue, particularly in the saline environments of the state and the wheatbelt areas in particular. So concrete alkalinity protects the reinforcement from corrosion, but when moisture, air, and or chloride ions above a certain concentration can penetrate through the concrete to the reinforcement, this protection that they have around them actually breaks down and corrosion commences in its initial stages. So it may appear just as rust stains, as you can see on the left-hand photo here. But then the expansive nature of the advanced corrosion to the reinforcements, it's in the order of 4 to 6 times its original size. So what happens is you then get cracking, delamination, and ultimately spalling off of that concrete, and then you get a heavily corroded reinforcement that's no longer protected from the environment. So these are some photos here of some culverts throughout the state, predominantly in the wheatbelt and WA. Another one I wanted to show you was spalling. So spalling is just a fragment which has been detached from a larger concrete mass, and you can see a couple of examples here. It's usually a continuation of the corrosion process, and it represents a serious defect because it exposes the reinforcement, and you've now lost your cover. There are other material defects which I'm not going to go into a lot of detail today. Things like delamination. So I referred to that before, where you have a discontinuity in the surface of the concrete, so that it's just before you get the spall. You can usually tell that you've got delamination by whacking it with a hammer, and then you get a hollow sound behind. You can see areas of dampness, and that might be a sign that you've got an indication of moisture penetration through the concrete. It may eventually lead to corrosion of the steel. It may be nothing, but it should still be looked at. Scaling is localized flaking or loss of surface of the concrete, and usually to a small depth. And that's prone in usually poorly finished or overworked concrete, where you have too many fines and not enough trained air that you found near the surface. So it can be superficial, and it usually doesn't extend to the reinforcement, but it may again lead to reduction in overall durability because you've lost that cover concrete. And then there's the things that most of us know about surface defects in concrete. So they're not necessarily serious in themselves, but they're indicative of a potential weakness in the concrete. So things like cold joints, honeycombing, efflorescence, and erosion, those sorts of defects, which are also important, but not necessarily the focus of this particular study. Then we have some defects that are generally related to the culvert site rather than specifically the box culvert barrel itself. So things like scour, vegetation, debris, drainage, movement, settlement, not really considered as part of this study at all, but loading has been. So loading is another defect, or another another thing that can cause defects. During construction, it's important, obviously, to make sure that you don't overload a structure as you put the backfill in, but also obviously in service. So impact overload at the slab edges, or where you have limited cover, are issues that may affect these precast box culverts. So comparing theoretical load carrying capacity to actual, as well as the failure patterns, is also being looked at by Curtin. So that's it from me. Hopefully that helps to set the scene a little bit and explain the problem and the size of the problem. It's fairly large in WA and throughout the world in terms of culvert structures and durability. As was said, happy to answer any questions at the Q&A in the end, and now over to Prabir for the more technical researchy bits.
Thanks, Erica. Yeah, as you pointed out, WA have got a problem, but I think most transport infrastructure organisations have similar issues. Our next speaker is Prabir. Prabir is a professor of civil engineering at Curtin University, Western Australia. His research expertise includes concrete durability, sustainable utilisation of waste and industrial byproducts in development of low-carbon construction materials and geopolymer concrete. He's the author of over 200 technical papers, and his publications have been cited over 20,000 times in Google Scholar, with an H index of 60. Prabir is a chartered professional engineer and fellow of Engineers Australia. Over to you, Prabir.
Thank you, Gavin, and thanks, Erika, for the introduction of the topic. Am I audible?
Yes,
Gavin?
yes, and I can see your presentation as well.
Okay. Okay, thank you all, and good day, and thanks all for making time to come to this presentation. And so this project is on investigation of the durability of precast concrete culverts. This is the team, the Curtin University. From Curtin, we had Shaugat Humagan, Mohammad Zaman, Chinmoy Datta are the HDR students working on this project. Myself, Wensu Chan, Faiz Sheikh, and Shihong are the academics in this project. And also from our industry partner BG&E, we have Daksh Baja, Peter Coglan, Erika Smith, and Greg involved in this project. Also acknowledge that this is a Smart Grid CRC project, and the culverts that we have studied are from the infrastructures of main roads. We acknowledge their contribution, and BG&E as the partner, industry partner. So Erika has already introduced the topic and discussed about the significance of the problem. So these are some of the contents that I will go through. Basically, I'll share some of the results of the study that we have done at Curtin. So that includes some site visits, 3 site visits, level 1 site visit, and then some more details, and also a visit to do some on-site testing of the culverts on corrosion activity and electrical resistivity, and also the core sample that we collected from the sites and tested in the lab to determine the chloride profile and relate it to the observed corrosion activity. And then we have also done some work on testing of some culverts, new culverts, to look at the load capacity, and then we have also done some work to look at the repair materials. So these were the subject of the 3 HDR students. So I acknowledge the hard work of the students that have put on this project. And if I cannot answer some questions in details, I will need to ask them. We have Atauz Zaman and Chinmoy here today. Shaugat is not around because Shaugat is traveling. So this is a map of the road network of main roads in WA in black lines, and and which shows the culverts in pink and green. The pink culverts are the precast concrete culverts, and the green culverts are the other types of culverts. So we can see the predominant type of culverts are the precast concrete culverts, and that is the subject of this study. We see that the water logging in a culvert. So this is from one of the site visits. We collected some water for testing to find out the pH and electrical conductivity and salinity of the water. So the field investigation, how we started was started with 1,400 visual inspection records that main roads Western Australia had. So to understand the majority type of the deteriorations, so common defects as Erika mentioned, corrosion, concrete spalling, delamination, erosion, and scaling. Then from there, 53 culverts were identified with the discussion with BG&E, and we observed the deterioration a bit in more details, and we collected the level 1 inspection reports from main roads to look at more details into those. And from those 53 culverts, we selected 14 representative culverts for further field investigation based on the severity and deterioration and accessibility. So this shows the location of the culverts in the wheat belt region in different areas of the region. So what we did is that we went to the site 3 times because the water in the soil varies seasonally. So we went once in May to collect some soil and water sample, and also to do some visual observation of the inspection of the culverts. And second site visit was in September, and the third site visit was done in a dry season on 3 culverts, 1, 13 and 14, to do some detailed investigation using the on-site testing, and also to collect core samples to test in the laboratory. So visual observation shows this salt tolerant plants in many sites, which is an indication of the high salinity, because these plants thrive in high saline soils and waterlogged conditions. So this shows from the visual observation that some culverts exhibited construction related deficiencies. Some shows like insufficient cover, say in culvert numbers 13 and 14 of our selection. So you could see in the right hand side that insufficient cover, so corrosion was obvious there. And also some culverts were found to, old culverts were found to have round shape aggregates. So we know that doesn't give very good interlocking of the aggregates, and can affect the strength and permeation of the aggressive agent into concrete. Some culverts had tapered legs, tapered at the bottom. So the thickness of the culvert leg was large, high at the top, but it was less at the bottom. So gradually decreasing towards the base, and also the backfill heights in culverts varied. In some culverts, backfill height was very small, so that can affect the load distribution of the traffic to the culvert. And so this shows the some of the deterioration that Erika already showed. So I will not go through this. Just it was the photos are taken from the inspection of the sites. So now the site exposure assessment based on the test results of soil and water collected from the sites. So using pH meter and electrical conductivity meter. So soil pH ranged from 6 to 9, indicating an alkaline condition. And like W government for industries and regional salinity classification recommends that salinity classes um, um, are high for the values from 58 to 114 millisiemens per meter, and 115 to 228 indicates severely high saline, severe saline, and extremely saline is higher than 228 millisiemens per meter. So on the right hand side in this diagram, we can see 7 uh, uh, sites out of 14 inspected categorized as extremely saline sites. So we can see salinity. This is actually based on the electrical conductivity, millisiemens per meter. So pH of the water ranged between 7 and 7.5, so indicating alkaline condition as well. And water collected from the site was tested for electrical conductivity, that also ranged from 2,230 to 8,600 millisiemens per meter, showing again extreme saline condition. So both soil and water test indicated extremely high salinity in almost half of the sites that we inspected. So soil and water samples were also tested for sulfate, magnesium, and chloride contents in the chem center. And the results shows that the results were used to classify the exposure condition according to S 5100.5, and what was found that 9 out of the 14 culvert sites were classified as exposure class C, which is C1 and C2. We can see on the right hand side diagram. And water with up to 6,500 ppm sulfate and up to over 3,000 ppm magnesium was found in the water. So chloride concentration was very high, up to 83,700 ppm, which is approximately 4.5 times of the chloride content of seawater. So you could see that in some of the sites they were very aggressive condition in terms of sulfate, magnesium, and chloride content. Then in the detailed third inspection, we went to the site to do some tests for carbonation and electrical resistivity at the site. So the carbonation depth was measured on the core samples. So core samples were collected from the good areas of the legs where there was no obvious deterioration, because core samples couldn't collected if there was already spalling or delamination. So then carbonation depth was tested by spraying 1% phenolphthalein solution, and higher carbonation depth was found at the top of the culvert legs, and minimal carbonation was found at the bottom of the culverts. The reason is the bottom part was had high moisture saturation at the base, which limited carbon dioxide ingress. So if we look at the results, we can see that culverts in the culvert legs above the flow line had a high carbonation, and below the flow line had low carbonation. So for the three culverts presented here, we can see in some culverts the carbonation was like up to 15-16 millimeter depth. In some other culverts it was up to like 8 millimeter, but at the bottom of the culvert it was very low. So if we look at the carbonation, so we can see carbonation was not the dominant type of durability deterioration mechanism, but it was basically the chloride induced reinforcement corrosion, as indicated by the very high salinity and moisture rich environment with limited carbonation. So electrical resistivity and corrosion rate plots along the culvert legs. So the limitation was that at the top of the leg there is a hunch, and at the bottom usually there was a scaling or siltation or some erosion. So that part has to be excluded. So basically the electrical resistivity and corrosion rate were measured in the middle part of the culvert legs, And of course, that was done where there was no obvious deterioration. So we needed a good surface for this for fitting of the instrument. And the observation was that there was low electrical resistivity and high corrosion rate near the base that we can see in this diagram. So the horizontal axis is the height from the bottom of the leg, and the vertical axis is the electrical resistivity on the left hand side, and the rate of corrosion on the right hand side. So the red line shows the corrosion activity. So we can see at the bottom of the culvert leg, the corrosion activity was very high, and it was decreasing as we moved up towards the top of the culvert. And the electrical resistivity is just the opposite trend of the corrosion rate. So the CIA Z7 practice note, Concrete Institute of Australia classifies the corrosion current density values of above 1 microampere per centimeter square as indicative of high corrosion. So you can see indication of high corrosion in some of the culverts. So this is the culvert number 14. Okay, it was different because we investigated only 3 culverts in this stage. So this is one of the culverts. The chloride profile of the core samples that were collected from the site was tested in the lab, and we plotted the chloride profile. So the horizontal axis is the depth from the surface towards the reinforcement, and the vertical axis is the total chloride content as a percentage of the mass of concrete samples collected from the core. It was tested in every 5 millimeter depth of the concrete, and what we see from this graph is that 2 lines. The red line is the dry upper region, coarse collected from the dry upper region, and the uh, blue line is from the flow exposed regions of the culvert legs. So you can see in the upper region there is less chloride compared to the lower region, because the lower region was subjected to alternate wet and dry cycles of the water carrying high salt contents. Okay, so the high chloride ion concentration confirms that the reinforcement corrosion was the primary mechanism of primarily driven by chloride ingress, the corrosion. Okay. Then, so from this, then we move to looking at the improvement. So in the up to the last slide, we briefly presented what was the result to understand the mechanism, the main mechanism of the corrosion. Then from here, we then looked at what could be done to improve the corrosion resistance and the deterioration and improve the durability of these culverts. So one way was to look at effect of supplementary cementitious materials on the steam cured concrete. We know that there are a lot of literature available on the effect of supplementary cementitious materials like fly ash, GGBFS, silica fume, and other type of SCMs on normally cured concrete, but there was less literature on the effect of this SCMs on steam cured or concrete subjected to accelerated curing, and that is the precast concrete. So we looked at looked at the effect of some SCMs like fly ash, GGBFS, and one of the new types of emerging SCM is DBS from the lithium refinery residue. So we know that fly ash is going to be scarce in the future due to the closure of the thermal power plants. So DBS can be considered as an alternative for the future. So we included DBS in this study. So some of the tests that we have done are like accelerated corrosion test, rapid chloride permeability test, and chloride diffusion test to see the effect of these SCMs on the steam cured concrete that is commonly used for precast concrete like culverts. So this shows some of the photos, and this is the chloride diffusion test setup. And so what was done was we limited the percentage of SCM in the concrete for the test to 20% cement replacement due to basically consideration that for precast concrete we need some minimum strength development in 1 day for demolding, and also a good strength development for transportation of the units to the site. So basically to the early age strength development of concrete. So for that consideration, we limited the SCM content to 20%. So what results was basically very briefly found. We have not shown all the results here, but the details results are can be found in some of our publications which are publicly available. So basically what was found is that fly ash and DVS was more effective compared to GGBFS at this 20% replacement against chloride ingress and reinforcement corrosion from this accelerated corrosion tests. Next, we just move to the load testing of some of the culverts. So the reason for this was to um, investigate the effect of these deteriorations at the site on the load capacity of the existing culverts. So we wanted to develop a numerical method that can predict the behavior of the structures, culvert structures, including the load deflection response and also the failure load. We so that this deterioration, like estimated section loss by deterioration and also estimated reinforcement loss by corrosion, can be uh, included in the numerical analysis to predict the um, uh, load capacity of the existing structures. So this needs validation of the numerical method by some test results. So we collected some new culverts, and also we are fortunate to get two old culverts from main road sites, and we tested those culverts in the lab. This shows the testing of the culvert according to the Australian standard. And what was found in all these culverts, all the failure finally occurred by punching shear of the slab where the load was applied. And the application of the load was a concentrated load in one of the sides in the mid span. And we see here a typical failure by the punching shear. This is where the load was applied. It shows some simulation by the finite element analysis using the Abacus software. So a model has been developed that can predict the load deflection response and ultimate capacities with the crack pattern and failure modes reasonably well. And we also looked at the comparison of the test load with the estimated punching shear capacity calculated by the Australian standard for the slab. So this diagram on the right hand side shows the comparison. So we can see that comparison with the test load at failure and finite element analysis prediction by Abacus, and also the S3600 punching shear prediction, capacity prediction. So we can see that the load capacity at failure could be estimated, predicted with good accuracy, which is close to the test failure load, and the punching shear capacity of Australian standard is generally more conservative than the finite element analysis. Next, we have looked at the use of repair materials, mortars to repair some of these deteriorations, and to see that if it could be a way to extend the service life of these culverts that are being deteriorated. So we investigated the mechanical properties, bond strength, shrinkage behavior of some polymer modified fiber reinforced mortar in the lab. So some of the mortars that were trialed in the lab was cement based mortar with a water to binder ratio, water to cement ratio 0.35, and a liquid styrene betadine rubber SBR polymer was added to it, and also a microsynthetic polypropylene fiber was added. So from and a high range water reducer was used. So from many trials, what was found is that so these results of the compressive strength on the right hand side, and also the shrinkage behavior of the mortars are presented in the diagram at the bottom. So what was found was that with the polymer SBR, compressive strength actually went down, but that was partially mitigated by the synthetic fiber. And what was found from this study was that 2% SBR and 0.5% fiber actually produced a motor that satisfied the EN 1504 compressive strength requirement of 50 MPa. There is a requirement for 1 day and 28-day compressive strength, which is presented here. So the first set of results are the for control motor, and the third set of results are for 2% SBR and 0.5% fibers. So we could see that it reached 53 MPa at 28 days and 28 MPa at 1 day strength. So that satisfies the requirement for a repair motor, structural repair motor. And that also improved the drying shrinkage, which is other very important parameter that is required for repair motor, because the shrinkage, high shrinkage will produce cracks at the early age of the repair, so which may not be very effective. Then we also looked at some of the commercial mortars, structural mortars available in the market. We looked at many commercial mortars, looked at their data sheet to look at their properties, and from there we selected 3 mortars that are produced and marketed by very prominent producers. And we looked at their behavior, and including again bond strength, mechanical properties, and also we are doing some durability related tests currently in the lab to compare. So we can see the comparison here again. Okay, so this is yeah, this is still the motor that we produced in the lab. So what we see here is that bond strength and flexure strength both actually increased by the combined use of the SBR and the fiber. So next page is about the commercial motor in this slide. So we are again looking at mechanical bond and shrinkage behavior of some of the commercial motors here, and these tests are ongoing. We got some results, but we are not producing all here. So basically we see that there is some variation in terms of the durability performance and mechanical strength and bond strength of the commercial motor. So hopefully that will give some comparison which will be helpful to select commercially available motors for repair of the culverts. So finally, we have so far presented briefly some of the results, not all of these, but the detailed results can be found in some of our publications. So if we draw some recommendation for durability improvement based on this study, we can say that from the physical observation of the culverts, so I found that some of the culverts are tapered, and it has the lowest thickness at the bottom of the legs, and we have seen that that is also the most critical location in terms of soil and water salinity and high corrosion activity. So probably these tapered legs reduce the cross section, reduce the cover depth to the reinforcement, so that could be considered in the construction stage, whether this tapered leg can be avoided, or which may increase the cover to the reinforcement and improve the overall durability of the culvert. And use of supplementary cementitious materials. So we have seen that these supplementary cementitious materials for concrete subjected to accelerated curing improved the permeability and the chloride diffusion. So that is probably not used as much currently in the production of the culvert, so that can also be considered to improve the material properties of the concrete, which may improve the durability of the culverts. And repair, so we in our inspection we actually didn't see any sign of the repair attempt of these culverts that are subjected to severe deterioration. So especially the culverts which are large, which has adequate access for repair, they may be considered for repair at the early stage of deterioration, which may increase the service life of the structure. So these are some of the recommendations. The study is going on. All the 3 HDR students are working on this project. So this is the recommendation based on the study that we have done so far. So some of the references that we used, and thank you very much for your attention.
Thank you, Prabir, and thank you, Erica, for your introduction as well. We'll open it up to questions. As I said before, if you have a question, please use the icon to raise your hand, and when I get to you, could you just state your name and organization and then your question. Likewise, if you want to put a question in the chat, I'm happy to read that out on your behalf. While you're doing that, I've got a couple of questions myself, Prabir. With the DBS, what were the percentages of DBS that you used in your mixes?
Okay, thank you, Gavin. Yeah, so it was 20%. So in our study, we just kept it 20% for all the 3 types of SCM. So they can be compared, the results can be compared, and also did not go for a very high percentage, considering that that may reduce the early age strength. So 20%, yeah.
Yeah, that was my, I suppose, subsequent question. As any other impacts, so they appear to improve durability, but were there any other than early age strength reduction, were there any other detrimental effects associated with the inclusion of DBS?
Early age strength, no, we did not observe any other negative effect of the DBS. So yeah, the workability of the concrete was fine. We looked at shrinkage results in other studies, that was also okay. So we did not notice any other negative impact. So apart from this, this study was limited to accelerated curing, steam curing. So we also did in other studies, we used DVS for normally cured concrete as well. Yeah. So those are some publications that we have been available in literature as well.
Okay. Just see a few questions coming in. One from Liam Devlin. Why use SBR and at that dose? SBR is more subject to UV degradation. Is the dose of SBR as dry weight on cement or liquid on cement?
Okay, that was, I think it was dry weight percentage of the cement. And maybe we have Chinmoy, the student who was working on it directly. I think Chinmoy can convert. Is Chinmoy,
Yeah,
are you here,
hi,
Chinmoy?
I'm
Yeah,
Chinmay.
yeah.
Yeah, and thank you. Uh, I've selected the SBR because in literature I found that the SBR is using to increase the durability of a motor for repairing, and it was in some literature they showed that it's providing good result in terms of durability. And I used the SBR in percentage of mass of cement. I replaced 2% of cement and added that mass of SBL liquid to that polymer, to that mortar mix. So
Oh,
the result that have been showed here, it also provided that uh, the bond strength also increased when polymer and fiber was included together, and also flexure performance was good, strength was good mm, compared to the standard requirement.
okay, thank you, Chinmoy. Yes, so yeah, so SBR, we cannot use too much SBR that reduce the strength. So it was limited to that value only. And yes, we noted the comment that the UV sensitivity of the SBR. We haven't done any test on that, so we note down that comment. Thank you.
Another question here from Iftikhar Alam. Did the culverts investigated have the required clear cover and concrete properties as per AS 5100? Probably a wider question than that, Prabir, was those culverts that you selected were in fairly aggressive conditions, and the pictures, I assume, came from those culverts with quite a bit of deterioration. Were you able to determine how old those culverts were?
Thank you. Riyam, it was very hard to find the exact age of the culverts because we tried to find that information, but exact age was we are not able to find. But we could say that some of the culverts were like 25 to 40 years old.
Okay.
So they, yeah, in most cases they followed the requirement at that time,
Yeah.
when they are produced. But as we have seen, some of the culverts they had like construction defect of not enough cover as well. So yeah.
Yeah.
Yeah, I think the other point to make is that from what Prabir said, the codes have changed obviously since they were put in service. That's one thing. The salinity is also a lot higher than that would have been expected at the time. So the culvert specification points you to AS 5100 for the exposure classification, and nowadays, the code nowadays also aims for a 100-year design life, whereas older codes were really aiming for 50-year design life. So their covers would have been a lot less, but the environments here are also a lot harsher than probably what they expected.
Yeah, just checking to see if there's any further question. There's quite a discussion going on in the chat. Look, I suppose another question, Prabir, was related to when you classified those exposure environments. Did you look at or did you find any degradation associated with sulfate attack? I'm just sort of alluding to that there appeared to be, when you showed a culvert with the surface scaling and the like on it.
Yes, Gavin. Yeah, so
Yeah.
the sulfate was found very high as well, and what was it? Yeah, somewhere. Actually, the student who worked on it, Shogat, is not available here today. He could have answered more in more details. But yes, sulfate from the site, from the soil and water was tested in Chem Center together with magnesium and chloride content. And I think sulfate content of the core concrete was also tested. And we are doing some test on the sulfate exposure of the concrete samples in the lab. So that is the new concrete using the different types of SCMs to look at the sulfate resistance of this concrete using 3 different types of SCMs and subjected to accelerated heat curing.
Very good. Another couple of questions in the chat. Prabir, one again from Liam Devlin. Did you measure the air content of the concrete?
Air content, no, we haven't measured air content.
Yeah.
Liam, is Liam meaning air content of the concrete that we cast in the lab or air content of the culvert concrete?
Of the repair mortars that you tested in the lab. And the reason I asked the question is that SBR is known to cause a problem with air entrainment. I did a lot of work with it in marine concretes many years ago, and that was one of the big problems they had.
Right. No, thank you for clarifying the question, Liam. So I again ask Chinmoy. Chinmoy, did we do this test, air content?
No, I haven't done this test,
Okay.
but also the SDR has problem with air content. When I have done my test for compressive strength and some my test analysis, in that case, I found that there were some void. But when I added the fiber, it was reduced compared to uh, when it was only the SDR, it was more fiber air content, but when fiber was added, it was mitigated.
I would suggest very strongly that you look at the permeability of water under pressure by BSEN 12390-8, because air content, depending on whether you create a connected or a disconnected air void system, can really badly affect permeability. The air content by itself is not a problem if the bubbles are small enough.
Okay, thank you, Liam, for the comment. Yeah, I think we have that test facility, Chinmoy. So please take a note of this. We haven't done that, right? Chinmoy?
No, I haven't done this.
Yeah. Okay. So maybe that could be checked. Yeah.
We got a question from Voot.
Yes. Good afternoon, everyone. It's Wood from UTS. This is a question for some of the manufacturers who are, I think, in the audience. The question is whether this day with the production of precast culvert, are there SCM introduced into the concrete, and usually what type and what level of SCM are used in our precast concrete culvert?
If there's no other manufacturers on board, I'm happy to answer.
All right. I noticed a lot of people from Hooms in here. No.
Yeah.
Hello.
Go ahead, Jason. Yeah.
Yeah. I put a little note in the commentary. Yeah, up to certainly 50% slag is able to be done, and is done. In culverts, I've seen it done in culverts. We've certainly done it on tunnel lining segments and the like for infrastructure work. So, yeah, that was my suggestion in the comments. Is, you know, taking the slag up to 50 or higher is quite reasonable because it doesn't seem to impact the early strength very much. When you're heat curing.
Yeah, I agree very much with you, Jason, especially looking at the analysis of the water and so forth. But just a question on whether they are actually available in the marketplace, I guess.
Mm-hmm.
We're just on time here, so maybe if there's one final question. No. Okay, look, we'll draw it to a close there. Thank you once again to Erica and Prabir for very thought-provoking presentations there, and wish you well with the continued research with you and your team, Prabir. Thank you.
Thank you very much all for coming and contributing with the questions and comments. I appreciate that.
Thank you.
Thank you.
All right. Thanks. Bye. Thank you.